So, welcome to this mini clip on ancestral character reconstruction. I'm Raphael. This is part of the tree thinking section for the crash course in evolutionary biology. So, what does ancestral character reconstruction mean? That's a method in which we are trying to infer, given that we know the traits that some species that we're interested in have at present, and given that we know the phylogenetic history of those species, so we have reconstructed their phylogenetic tree. We want to be able to reconstruct what were the values of that trait we're studying, or a given character in the past at the nodes of the different ancestors so the nodes in this phylogeny, uh, and how basically did this trait evolve also along the branches of this phylogeny. So there are different ways to go about this. Every time we're using basically mathematical models to go about that. So if you remember in the clip on phylogenetic comparative methods, we said that sometimes to account for the phylogenetic relatedness of species, we use an underlying model of trait evolution along the branches of a phylogeny, some simple models like a Brownian motion model. And this is exactly what we can also use here for ancestral character reconstruction. So we could basically pretend that the spread in trait values that we're observing between our species at present is the result of a relatively simple model of evolution of the trait along the branches of the phylogeny. In the case of the Brownian motion model, it would be a random walk. Where the trait value basically we assume that it has stochastically diffused through time to get to the present and to the distribution of traits that we see in our data set. Now, this is a stochastic process, a stochastic model that we're assuming. So we're assuming that it's a what we see is a realization of this stochastic process that involves a lot of random movements along the way, of course. And that's going to become useful in a minute. But first, I want to say that, well, this is for a continuous trait sort of case, but of course, this could also be performed when a trait that we're interested in reconstructing the ancestral state for is a discrete trait. So, for example, this could be all kinds of categorical traits, right? Like the presence of limbs in lizards, for example. Um, so some lineages of lizards have limbs, others don't, and we may be interested in reconstructed. Okay, when did lizards lose their legs? Which lineages did lose their legs, and what sort of characters did those ancestors have? This kind of like discrete trait reconstruction would also involve some mathematical models, except that now we would not have a model of continuous evolution along the branches of a phylogeny. We would assume that those traits, discrete traits, are also evolving along the branches of the phylogeny, but according to some transitions that could be described or captured by a matrix of transition rate. And that should remind you of the matrix of transitions between different nucleotides in the lecture when we were reconstructing phylogenies. It's a little bit similar. Except now we are assuming that we know the phylogeny, we have reconstructed it, and now what we want to do is to map onto it the evolution of the traits, the transitions from one discrete trait to another, for example. So in the example that we're showing here, the intensity of the color in the matrix basically represents the intensity of the rates, the how high the rate of transition from A to C, from A to B, for example, is uh, on a per million year basis. So again, we assume a stochastic process generated the distribution of data that we have in our data set, and that this stochastic process unfolded with certain rates that are captured in this matrix. Now, whether use the sort of we are using continuous trait models or discrete trait models, both in both cases we are using stochastic models. And as I said before, this has the advantage that we can use some probability theory to basically fit the model to the data. And how do we do this? Because hopefully we can come up with a likelihood function for our model, whether it's a continuous trait model like the Brownian motion, or whether it's a discrete trait model with a matrix of transition rates. We can use the likelihood formula assuming that we can come up with a formula for that likelihood. So the model that we're using should be relatively simple so that the math can be figured out for that formula. But assuming that we can do this, then the likelihood, so the probability of the data given the model, so here the data would be the representation or distribution of traits at present, whether it's continuous or discrete, given the model, and the model would basically be either this Brownian motion in the first case or a transition matrix in the other case. We should be able to compute this likelihood for lots of different variations of this Brownian motion model, for example, with lots of different rates of evolutionary change through time, for example, or in the case of discrete trace, we could compute this likelihood for lots of different values of those rates in this matrix. And if we can do that, then we can use some sort of maximum likelihood algorithm, just like we did in the reconstruction of phylogenetic trees, to pick basically what is the matrix of transitions between A, B, and C that best explains our data set, or what is the rate of evolution in this Brownian motion that best explains our data set. Now, just like with the phylogeny reconstruction, we can impose some constraints and variations on the models that we're using. So we could have like some specific versions of the discrete trait evolution and say, for example, that the rate of transition must be symmetrical, for example. The probability of transitioning from A to B along the branches of the phylogeny is equal as transitioning from B to A. In the continuous trait model, we could say, yeah, well, Brownian motion is a bit too simple a model, and use something like an Ornstein-Uhlenbeck model, which is a model that assumes also relatively simple, but that assumes some sort of random walk, but that stabilizes around some optimum value. So it's kind of modeling in a very simplistic way the evolution of a trait subject to an evolutionary attractor, so a trait subject to stabilizing selection. It's basically up to you to choose the kind of model that you want to fit. But of course, as often in statistics, if you fit different models, then you will have to compare the fit of your model. So if you have fitted to your continuous trait data, for example, a Brownian motion model and an Ornstein-Uhlenbeck model, you may want to compare, okay, which one has actually fitted my data the best. Usually to do this, you compare the likelihoods, but not just comparing the raw likelihood. Usually you use some penalized versions of this in a very common way of doing this is the KIK information criterion, this AIC. So each once a model with a given likelihood function has been fitted to some data, it will produce an AIC, and basically you can compare the AIC of the Brownian motion model fitted to your data to that of the Ornstein-Uhlenbeck model fitted to your data, and pick the one that gives you the best AIC score, so the best goodness of fit. That's called model selection. You would basically do this to pick the best representation of what may have happened during evolution that gave rise to the data set that you see today. And once you have identified the best model, for example, using the AIC criterion, you can come up with a story about how you think that your character has evolved along the branches of the phylogeny. So you can show basically what the conclusions of the best fitting model is saying. So in this case, we have an ancestral character reconstruction of a continuous trait in anolis lizards. And you can see that the colors along the branches of the phylogeny represent what the model infers the trait may have looked like in the past as you go back along the branches of the phylogeny.